we're going to give you one more example now of a convolutional code, and this code will take you through the encoding and the decoding process again, try and take you through all the steps. Give you one more example. We'll change it up a little bit. We'll make the coding rate 1/3 as opposed to the previous example, which is always 1/2, but we'll keep the same constraint length 3 because we don't want to have our states get too big. It just gets a little hard to manage. So we're looking at this example, and as I said, we're going to have k, the constraint length, equal to 3. I'm only showing you the two registers which represent the state, but of course there's also here the input buffer, which would be the third shift register for when I put in my data. But here we'll just show the two state registers. Now there's 3 outputs because I have a rate 1/3. And in the first case, we have here the vectors that represent the interconnections for the registers to generate the codes. I notice also here the list of the hexadecimal representation for this binary number, which is another way you can sometimes see codes listed in a table of codes. They might give you the vector, or they might just get you the hex representation. Now, the first one here, G1, is just simply this interconnection, which means that it's just taking the input vector, just looking at the input vector, not combining anything with it, which means this is a systemic code. I can read the data bit directly inside of the code. So as the code words come out, I'll know that the first bit just represents what was the input to the encoder. Now the other two data bits, of course, are derived from these 3 registers. And in case of the second bit, you're adding the input buffer with the first register from the state. And in the third one, we see the summation, and there's from all 3. So all 3 of the registers are going to be added to generate the third bit of the code word. Okay, so now let's go on to the encoding operation. And once again, I'm going to define 4 states. I think I changed the order of the states a little bit. The first state, A, is always the all 0 state, and then I think this used to be what we called C, this used to be what we called B, but it's really completely arbitrary. So now B is the 0, 1, C is 1, 0, and the last state, of course, is 1, 1 in these registers. So we've defined our states. Now we're going to build our trellis, and to build our trellis, we look at our encoder and we say for a given state, like if I start at 0, 0, if I input a 0, well then of course the summation of all of these is going to give 0, so I'm going to get the 0 code word again. Suppose I'm at state 0 and I put in instead a 1, what's going to be my output then? So I'm saying I'm at state 0, so I have a 0 here and a 0 here, and then I input a 1. And so the first output, of course, is going to be the 1 because it's a systemic code, so the first one is 1. And if we look at the next one, it's a combination of 1 and 0, and that gives me a 1. And then the last one is, of course, a combination of all 3, 0, 0, 1, gives me another 1, and I get the 1, 1, 1. We could take any other entry in the table, see if we could maybe run that one more time, see how you would fill up a trellis based just on the implementation. So for instance, say I started at 1, 0 and I look at the 0 transition. So here I am at the 1 and 0 state. So I'm at the 1, 0 state. I enter in a 0. So I have a 0 at the input, and I calculate what is the output for, first of all, systemic. So whenever there's a 0, the first one is 0. You know, all the red ones, the first ones start with 0. All the blue ones, they all start with 1 because it's systemic code. Now, I look at what is the second one, and so for the second one, I see I'm combining 0 and 1. That gives me a 1 here. And for the last one, of course, I'm combining all 3, and when I combine all 3, I get a 1 again. So now you know when you're given the the shift register implementation, how you can generate the trellis for the encoders, and of course, it's also used in the decoder. So we have our basic trellis for the encoder, and if we build a complete trellis, we would just repeat this over and over. So here we have the repeated trellis, and of course we have our states. Okay, the constraint length is 3, which means we have 4, and then all the transitions are defined, and we have our code words at the output. So if I wanted to notice that n equal 3, that's because when I look at what are the code words, I have 3 bits in the code words. So that's directly from n equal 3. Now let's take the encoder and use it to find the minimal distance. So we want to know how good is this code. So this could, how are we going to find the minimal distance? Well, I'll try all the paths between something that starts at A and ends at A. And here I've taken the path where I start at A, I go down to C, then I go back up to B, and then from B I go up to A. And I calculate the weight of this code, or the distance between this code and 0, which is also known as the weight of the code. And that way I just add up the number of ones. There's 3 here, 2 here, 1 there, that makes 6. So the distance between this code and the all 0 code is of course the number of ones, because this is always 0. So the number of bits that are different are just the number of ones. And we call that the weight of the code. And for this path, it comes up to be 6, and I won't go through all the others, but you can try it yourself, and you'll find that indeed the minimal distance is 6, or we also call that the free distance for a convolutional code. Let's look at an example of how we actually do the encoding. We'll start with data input of 0. And I'm starting again, always starting at state A. If I input data 0, I'm going to stay at state A, which means the code word that comes out is a 0. Now let's suppose that the next bit that I input is a 1. So the next bit is a 1, which means that I'm going to go from state A down to state C. And the output from my encoder, I know that that will be 3 ones. And as if I go up now, have an input of a data of 0, now I'm going to go from state C to state B, and the code word at the output is going to be 0, 1, 1. And finally, if I input another 0, I go up to state A again. So this would be the path that represents these 4 data bits, 0, 1, 0, 0. 0, the red solid, 1, the blue dashed, 0, the red solid, red solid. So that path represents the path through the encoder. And of course, if I read the states that were included, or I could look at the code. So here we see the code that's transmitted. We have the 3 zeros, 3 zeros, 3 ones, 3 ones, 0, 1. So here I have the output of the encoder in terms of the code that's transmitted. And if I wanted to look at the states, how the states were changing, I was at A, then down to C, up to B, back to A. So we have a representation of the output of the encoder, the input to the encoder, and the states of the encoder during this process. So this is one example for encoding. Let's look at another example. This example is another path, and in this path we're going for initial state is A. Those are the first 2 zeros. Just means we're starting here at A. And now I have a bit sequence that's 1, 1, 0, 1. So I have 1, 1, 0, 1. And in this case, I would write my code. I would read the code here off of the path. The codes along the path, it would be 3 ones, that's the first leg of the path, 1, 0, 0, second leg of the path, etc. So I would know the output in terms of the coded output of the encoder. And if I asked what was the weight of this path, that would be the number of ones in the path. And if I look here, I would count 7 ones in this path. So if I were to ask the question, what is the distance between this path And the all zero path, well, that would just be the weights, but of course this one doesn't actually go back to the state A yet. But just for, in terms of definitions, to help you in answering questions on the exams, different kinds of questions that could be asked, this would be an example. Given the path, what's the weight, what's the distance to the all zero states, etc. So that's the encoder, how to build an encoder, how to start from the shift register implementation, or you could have started from the vector representation or a hexadecimal representation, built your own register, and gone through the encoding. Different kinds of questions I could ask about the encoding process. So now let's look at the decoding process, and in particular the Viterbi algorithm. And I'm going to give you an example now where we do a transmission with two errors in the transmission. So the true data one is the one I took you through the encoding of when we did a 0100. We saw that the transmitted codes in that case was this, and here we're going to see that the received codes are different. We're going to have 2 bits that were flipped during the transmission due to noise. And we'll see that despite these flipped bits, this decoder will still come out with the correct data sequence by using the Viterbi algorithm. So let's just step through that. So we know the original condition. We know that we're starting at state A. We have the received code. It was 01 during this first time interval. And so I start calculating. Here is my trellis from the encoder. And it tells me for each one of the transitions what is the code word associated with that. And in the first case, the code word would be all zeros for that transition. And for this transition, it's all ones. So I've formulated the possible transitions, and now I calculate for the decoder, I calculate the distance between the received vector and what were the good code words for each one of those transitions. So I calculate the distances, and I save the paths with their distance in memory. So in memory I would put that for state A, you got there due to a 0. And the length of this, we calculated the distance between all zeros and 01 is 1, so the branch metric was 1. And for this transition, of course, the branch metric is 3. And we saved this in memory. I'm sorry, the branch metric is 2. I'm very sorry. There are 3 ones, but there's a 1 here. So the branch metric is 2, my mistake. Branch metric is 2, and so that's what we save in memory. We save the path, that it was for state C that we came with a 1, and for state A that we came with a 0, and we save the path metrics. The path metrics in this case are just the branch metrics because the path is just one hop at this point. So we go on, go to the next received code. We take it down from here. What was received was 110. We put it here. And we start looking at formulating all the possible transitions. So I'm only either at A or C. So each one of those has 2 possible transitions. So I take them from my encoding trellis. And now I'm going to calculate again what is the distance between this received code and each one of the codes on these transitions. And so I say the first one is all zeros, there's 2 ones, so there's 2. That's the branch metric for this transition. And for the next one, 3 ones, 2 ones and a 0, so there's 1 different. Here, 0, 1, 1. So the first one's different, the middle one's the same, the last one's different, so that's got a weight of 2. So I've got my 4 branch metrics. Now I've calculated these branch metrics, the local distances, and now I calculate the distance for the global one. So I have this branch metric, and now I'm adding to that my reserved previous path metric. So now I had 2, and I came from a point that had 1 previously, so I know that sums to 3. Down here I came on a path, on a branch that had a metric of 1, and I came from a path with a metric of 1, so the new path metric is 2. Here I arrived at state B because of a path with a 0 on it with a length branch metric of 2, added it to this saved previous path metric of 2, so that gave me 4. So now I have new global lengths that I've calculated using the previously saved path metric and the newly computed branch metric. So again, I save in memory these values, which are the path metrics, and I save the path to get there. So I'm going to save 0, 0 as being the data sequence that got me to state A at time 0. And for state C, for instance, I'll have the 0, 1 being the data sequence that got me there. That's the path I'll save. So I've saved 4 paths and 4 path metrics. I go to the next transition, look at the new received code, and now I formulate all of the possible transitions, and now I'm in steady state. And now all 8 possible transitions are present, and from now on there will always be 8 possible transitions. It was just the first 2, they're sort of getting me up into steady state that we saw previously. So now I'm always calculating 8 values, and the first step is just to calculate the distance between this received code and each one of the transitions. So I compare them and get the Hamming weight for them. For instance, down here, the first one's different, the second one's different, but the third one's the same, so that will have length 2. And of course, I do that for each one of these paths, and I come out with the results here. The next step now that I'm in steady state is for each of the states, I'm going to have 2 path metrics that I'm going to have to compare. So now we can do add, select, compare. So we have this branch metric, and I'm going to add it to the previous branch metric. And I'm going to have here 2 values that I'm always saving. One is for what I call the lower path, came from down here, and one is from the upper path, came from up here. So in this case, let's take the first one. This transition is 2, and the previous state was 3. 2 plus 3, that gives me 5 on the high path. Let's look at the low path. The low path came from state B, where the previous path metric was 4, and now I have 1, so that sums to 5, and I write it here in the second column in blue for the one coming from the lower path. So I'm calculating the global distances, and I'm doing 2 for each one of the states. Here, for instance, if I came from state A, the branch metric was 1, the previous path metric was 3, I add them up and I get 4 for the upper branch. The lower branch, I came and it was a branch metric of 2, and the previous path had a length of 4, so it gives me a length of 6. So that is my add. I have done my adding of the current branch metric with the previously saved path metric. Next I do a compare. I compare these 2 to find which one is greater and lower. I keep the lower one. So here 4 is greater, so that's what I eliminate. It's the 2, the path that has length 2 that I save. 6 and 4, 4 is smaller, I save it. The other 2, they're equal. And then when they're equal, it doesn't matter which path I pick. They're equally likely, and so I just pick one of them and retain it, and the other I get rid of. So now that I've made my choice of which is better, here it is. It was the one coming from above that was better, so the one that came from below I've eliminated. The one that had length 4 is no longer present here. I got rid of it. And you can see that all of them have been pruned. I didn't prune these last 2 because I haven't picked yet, but I will pick now arbitrarily, and I'll just keep one of them. So in this case, I've gotten to the point where I have 4 paths, and there's no merge yet. There's no common point where they all come together. So I have 4 separate paths. So if I ask you, what is stored in memory at this point in the Viterbi algorithm? Well, there would be a memory, which is for state A, and in state A I would show that it was a 0, 0, 0, and that the current path length is 5. When I'm here at state C, I would say that there was a 0, 0, 1 is the path, and that the path length is 4. So for each state, I have the data sequence up to that point and the path length. So I take these values, this is what's stored in memory, and I move on now to the next received code, 0, 1. And I do the whole thing all over again. I get back my encoder Trellis. I populate the transitions with the codes that would have been transmitted, and I compare them, this code, with the received one, and I calculate the distance. So now again I have the local distances, or the branch metrics, and I'm going to get two global distances for each of the paths going to the next state. And in this case, the upper paths, I have their length, and the lower paths, I have their length. And I'm going to, I did the add to get here, and the next point is to compare. Compare them, and we see that, of course, the 2 is smaller, 5 is smaller, 6 is smaller. Here they're both the same, so I picked the upper branch. But I've done the compare, and now I do the select. Which one I'm going to keep, the larger one, the smaller number, larger font size, is the one that I keep. And so now I cut the other path. And you can see that because I only kept the lower path, which had length 2, the upper path is no longer there. So this is an orphan. This will disappear. This will get pruned out. I can't prune this one out because it's part of this path that comes down. That's for my visualization. You can see that because I cut here, this whole path is going to disappear. So all of those go away when I prune out the less likely paths. So now when I get to this point 4, well, now I have a merge. Everybody agrees the first bit transmitted was a 0. So that could be output right away. Now if I was forced to make a choice between these 4 paths, which is the most likely? Well, this one has 2 errors. This has 7, 5, and 6, and the most likely is the fewer number of errors, and that would be 2. So this would be the most likely path if I was forced to make a decision at this point. So choose the smallest path. I look at all of them, and clearly this one with 2 errors. So you recall I had 2 errors in the original transmission, and now they've been corrected. So I thought that the code word was 001, but what was really transmitted was the code word 000, and that's where the bit flipped. Again, here I can see it was that bit that flipped. There were no bit flips. There's 2 errors in here. I can read them there. But that's not the data, okay? That's where the errors occur. But when I say I corrected the errors, the real way that I correct the errors is just by knowing which transition actually happened. So these code words tell me that's not where I read what was sent. Where I read what was sent is in this red solid line, blue dotted line, red solid, red solid. That gives me my 0 for the red, and the blue gives me my 1. That gives me my data sequence. That's how I can read the corrected sequence. So that concludes this example of the Viterbi algorithm, and this would be a way a computer would do it. Maybe not exactly the same way we step through it, but it does give you a feeling for the computation that's involved in the Viterbi algorithm. And you can see that in this case, there's not just 2 transitions, there's not just a higher and lower. I think in each one of these there's 5 different valid input points to each one of the states. And here they're evaluating each one of them. And as they evaluate, they keep only the one that is the most likely. And at the end, they go through and they prune the ones that were not retained. And we can see as the algorithm steps through how many are being pruned. And when we're getting to this last point, we have 3 converges already in our system.